Howdy everyone. Today our team is going to talk about supercritical CO2 power cycles. We will be covering its benefits, operation and continuing developments. I am Aditya and I'm going to begin with a brief introduction to supercritical carbon dioxide. A supercritical power cycle or power plant is a process that produces power from turbines using supercritical carbon dioxide. What is supercritical CO2? It is a fluid state of carbon dioxide that is above the critical point. At this point, the density is close to that of a liquid, which reduces the pumping power needed in a compressor significantly. Supercritical is a state in which liquid and gas phases are not easily distinguishable. Supercritical carbon dioxide is a state at which the temperature and pressure of the carbon dioxide are above its critical state. Now let's talk about the benefits. Smaller in size than systems that use steam. This is quite beneficial as it requires lesser area and also lower capital, therefore making the plant cheaper to build and operate. Increased efficiency. This results in increased electricity production for the same given thermal input. Improves the environment by the reduction of greenhouse gases. Any carbon dioxide produced in the process can be reused to generate power. This therefore reduces the emissions of carbon dioxide to the atmosphere. Water consumption is reduced significantly. A reason for this is that it would require far less water than a steam plant, as well as less water needed for cooling, therefore helping save vital resources. Enables dry cooling, thus making it easier to operate the plant in arid, dry environments when water is not readily available. Now, as you can see, here is a layout of a supercritical CO2 power plant. And in the next slide, I'm going to talk specifically about how a recuperator reuses the carbon dioxide. So here is a recuperator. And as you can see, hot waste gases, in this case, hot waste carbon dioxide, can enter the recuperator and heat any incoming fluid or gases, which can be used for the power generation process. So as you see, the carbon dioxide which is generated from the waste isn't really going for waste. It's actually being reused and put to good use, therefore reducing any emissions to the environment.
Everyone, I'm Saranj and I'm here to explain the working behind the supercritical gas as a working fluid for power generation. So before we get started, we're going to talk about some of the basics behind power generation. So we need to talk about solids, liquids, and gases. You guys are pretty familiar with most of the concepts, but one thing that I would like to highlight is solids are not don't have a lot of randomness because they are very tightly packed and they don't move around. Liquids, on the other hand, have much more randomness because there is certain spaces between them, and there's like the molecules move haywire sometimes, and gases are really random. So we use this property of materials along with several other properties and moving between them to generate power. And two of the devices that we use to generate power are a turbine and a compressor. So a turbine is basically an expander which produces work while doing so. So we push a fluid through and push a fluid out. So the pressure outside is in the outlet is a lot lesser than the pressure that is inside, like when we go through the inlet. And in the compressor, it's the other way around. So we need to compress the liquid, pressurize it, and we do so by providing some power to it. So those are the two main devices that we use. So a graphical representation of the states. So we can manipulate the states based on this graph and manipulating the pressure and temperature. So usually we operate in these two regions, but the limitations are that when we move between these two states, it causes certain mechanical failures of the equipment. So in our fluid, we use supercritical fluid. So at that high pressure and high temperature, we can operate. Liquids and gases are pretty similar, so we have properties associated with both of them. So like the density of the fluid is very much like a liquid, so the properties are pretty similar, but they don't change states. So that's why we operate in this region. And another thing that I would like to highlight is this is the net work that we do in such a cyclic process. So this area right there. So there is a lot of work produced in a process like this. Right. So we're going from state 1 to state 2 in this diagram, which is the cyclic process that we're following in power generation. So it's being heated, the supercritical carbon dioxide, to state 2, after which is passing through a turbine, which is extracting the work out of that heated fluid. After which it goes to state 3. There's not a lot of increasing in the randomness, which is the entropy, as there is no heat provided, so there's not going to be a lot of movement. So it's going to go to state 3, after which you're going to cool it down in a similar way as we heated it up. We're just going to cool it down, after which it's going to go to state 4. So we need to bring it back to the initial conditions to make sure that the cycle reaches its conclusion. So we're going to bring it back to state 1, which is going to be through a compressor. We're going to provide some energy and it's going to compress the liquid into the requisite parts. And so that's how the cycle works. So a key part of it is the efficiency. So as we discussed earlier, that this is just one state. So what we can do is increase this part of the diagram to expand further so that the T hot, which is the temperature at the hot side, it increases. So this factor becomes smaller and the efficiency overall increases, which is the end result that we want. So we extract a lot of working out of it, as you can see in this PV diagram as we discussed earlier. So that's the end goal. So we increase the efficiency using this model and we decrease the volume because the density is lower. It's acting like a liquid, unlike most of the cycles which operate in a similar way, which are acting in a gaseous way. And also carbon dioxide is chemically unreactive, so it doesn't react with metals. And it's good for the environment that we're using it in this way because it doesn't take a toll on the environment. And that's it for my lecture. And I hope Michael does a good job explaining the future technological advancements that are going into this project.
Howdy everybody, my name is Michael, and I will be taking you through continuing developments on supercritical CO2 power cycles. We will talk about the ways researchers are continuing to develop this technology to improve upon it. By improving upon this technology, reliance on fossil fuels can be reduced, helping move towards the use of renewable energy. Lower harmful emissions can be achieved, and a higher efficiency can be achieved to allow greater electricity production while also reducing electricity costs. There are 3 ways we're going to talk about today to improve upon the already efficient technology. Turbine blade cooling technology, which will allow a higher temperature drop, meaning a higher efficiency, developing components that can withstand wear and tear, and developing compact heat exchangers to recover heat in the cycle, meaning higher efficiency. The first way is turbine blade cooling technology. By allowing cooling of the turbine blades, reducing thermal stress on the blades, a higher temperature drop can be achieved. This can be illustrated by the equation shown. A higher denominator will result in a higher efficiency. Cooling the blades is done using air or liquid. One way is by convection, where heat is transferred by conduction through the blade, then cool air is distributed in the blades through convection. Another way is by impingement cooling, where the insides of the blades are hit with a high velocity air, allowing a high transfer to the blades versus convection. This method is usually used where the temperatures are the highest. The second way is more durable components. Different materials will react differently over time. Researchers are looking to find a way to balance durability and optimal mechanical performance. The material needs to be capable of withstanding high temperatures and pressures. In order to prevent corrosion and erosion, alloyed materials are preferred. It has been found concentrations of nickel and chromium have been found to increase corrosion resistance, and austenitic steels are also being used. They're a type of steel that has a unique crystal structure, and they have been found to be more CO2 corrosion resistant compared to the other types of steel. The final way is by improving the recuperator. The purpose of integrating compact recuperators, which are also referred to as special purpose heat exchangers, is to recover heat from the cycle that can be used again. By making improvements upon the heat exchangers, more heat can be recovered to be used. This waste/excess heat can be used to help the CO2 that is entering, thus reducing the amount of fuel required to later be used to continue the energy conversion process. The way the recuperators are becoming more compact is by using a different configuration of tubes. As you can see on the right-hand figure, that is the cross-sectional area of the tube, which is circular. On the 2 diagrams to the left, those are the configurations of the tubes. One is square and one is triangle. As you can see, the triangle configuration is more compact, so that is preferred. That will conclude today's lecture over continuing developments and overall on the topic of supercritical CO2 cycles. Thank you everybody for watching.